Imagine this: everything we know, every galaxy, every atom, every moment of time itself unfolding inside the shadow of something far larger. Not a metaphor, not a thought experiment, but a physical structure in space-time. A place where gravity becomes so intense that the fabric of reality folds inward and creates a world sealed from everything outside. For a century, physicists have asked whether our universe could be that world, whether we are living not in open space but inside the hidden interior of a black hole. It sounds impossible at first. Black holes, after all, are the great endings of the cosmos, the graves of massive stars that collapse under their own weight. But when Albert Einstein wrote down the equations of general relativity, he revealed something far stranger. Under extreme gravity, space does not simply compress. It curves into a closed geometry, a shape where time slows, distances distort, and beyond a certain threshold nothing can return. That threshold is the event horizon. To the outside world it marks the limit of existence. But the mathematics does not stop there. Inside, the same equations predict a region that keeps evolving, keeps expanding, as if an entirely new cosmos has begun behind the veil. In the 1970s, this idea was little more than an odd mathematical curiosity. Then, in the early 2010s, physicist Nikodem Popławski revisited it through an extension of Einstein's theory known as Einstein-Cartan gravity. This version of the theory includes one crucial ingredient that standard relativity leaves out: the intrinsic spin of fundamental particles. Spin might seem insignificant, but at density approaching the center of a collapsing star, it becomes powerful enough to twist spacetime itself. That twist, called torsion, prevents matter from being crushed into an infinitely small point. Instead of a singularity, the collapse reaches a limit, rebounds, and pushes outward. From our perspective, inside such a rebound, it would look like the beginning of a universe. Space expanding in all directions, time flowing forward, energy released into a newborn cosmos. It is a radical idea, but it has elegant consequences. It explains why the early universe was astonishingly smooth, as though everything had been in contact before expansion began. It explains why the total angular momentum of the cosmos is nearly zero, as if the spin of a parent universe had been balanced away. And it explains why the laws of physics appear finely tuned, not because they were chosen, but because they were inherited. Even the geometry inside a black hole seems to echo this picture. Outside the event horizon, time flows as we expect, and space offers freedom of movement. Inside, those roles switch. Time becomes a direction leading inward, unavoidable, like the next moment in a story. Space stretches instead of collapses. Nothing escapes, yet nothing stops. To an observer, within the interior is not a dead end. It is an expanding realm with its own timeline. If this interpretation is right, then our universe might be exactly that interior. Not the entirety of existence, but one chamber within a larger cosmic structure. Our Big Bang would not be the first moment of everything. It would be the instant when the core of a dying star in another reality rebounded and became the space-time we live in now. This perspective changes the deepest question in cosmology. Instead of asking, where did our universe come from, we must ask something even more profound. What universe came before ours, and what kind of star collapsed to create the world we inhabit? That question hangs over every observation we make, every galaxy, every photon, every echo from the early universe. If we truly live within the interior of a collapsed world, then the night sky may be showing us the unfolding of a story that began long before the first light we can see. Falling toward a black hole is not like falling toward anything else in the universe. At first, nothing feels unusual. You drift through space as if gravity were simply guiding you along a gentle slope. But with each kilometer you descend, the geometry around you begins to twist. Light bends, distances warp, and then without any visible boundary you reach a place where the rules of reality shift beneath your feet. The event horizon. Outside that horizon, space and time behave the way we expect. You can move in any direction through space while time carries you forward like a quiet current. But as you cross the horizon, those roles trade places. Space narrows into a single path and time becomes the force pulling you inward. No matter how powerful your engines or how desperate your effort, there is no turning back. The inward direction is not a choice. It is the future itself. This strange transformation is written into the Schwarzschild solution of Einstein's equations, the mathematical description of a non-spinning black hole. Near the horizon, the coordinate that once measured distance begins to act like time, while the coordinate that once measured time behaves like a spatial direction. To an observer on the outside, you appear frozen at the threshold, never quite crossing. But from your own point of view, you fall freely moving through a landscape where the meaning of motion has changed. Real black holes, however, do not sit still. Almost everything in the universe rotates, and black holes carry that rotation to the extreme. In 1963, Roy Kerr found the solution for a spinning black hole, and it revealed a structure far more intricate. Instead of a single horizon, a Kerr black hole contains two. Between them lies a region where spacetime is dragged around by the rotation twisted so violently that even light must follow the swirl. This phenomenon, frame dragging, turns the space near the black hole into a cosmic whirlpool. Inside this rotating geometry, pathways that seem impossible elsewhere become mathematically allowed. The equations admit tunnels of warped spacetime structures known as Einstein-Rosen bridges. In classical physics, those bridges would collapse the moment anything tried to enter them. But modern quantum models suggest that information passing through such regions may not be destroyed. It may transform, changing the very shape of the spacetime within. To visualize this, physicists use a different picture. The river model. In this analogy, space itself flows toward the center of the black hole like water rushing into a drain. Far from the hole, the river is slow and light can swim upstream. Closer in, the flow speeds up. At the horizon, the river falls inward at exactly the speed of light. Beyond that point, the current moves faster than light can escape. Not because physics is violated, but because space itself is the thing that is flowing. This perspective changes how we imagine the interior. A black hole is not pulling you in. You are stationary. It is space that is carrying you downward. Light is not trapped because it is weak. It is trapped because space-time is falling faster than light can climb. And at the center of this inward motion lies not a place, but a moment. A point in space-time that everything inside must eventually reach. Yet this does not mean time ends there. It only means that the direction we call future points inward instead of forward. From the outside, nothing escapes. From the inside, nothing can pause. The geometry insists on continuous motion toward the core, and here the big question emerges. If time inside a black hole flows toward a single destination, what truly lies at the end of that path? Is it a point of infinite density where physics breaks apart? Or is it something else entirely, the threshold of a new spacetime waiting to unfold? The equations of relativity cannot answer that question alone. They predict the collapse, but not what happens beyond it. To go further, we must bring another theory into the story, one that governs the smallest scales of nature where space-time itself begins to fluctuate. Relativity can take us only so far. It describes how gravity bends the universe, how stars collapse and how horizons form. But at the deepest point of that collapse, where densities rise beyond anything we can imagine, Einstein's smooth space-time can no longer hold. The equations predict a singularity, a place where curvature becomes infinite. And whenever a theory produces infinities, it is telling us something simple. It has reached the edge of its domain. To understand what happens beyond that edge, we must turn to quantum physics. In the quantum world, nothing is perfectly continuous. Energy, distance, and even time come in tiny indivisible units. At the Planck scale, 1 trillion times smaller than a proton spacetime does not behave like a fabric at all. It flickers. It foams. It becomes a restless sea of fluctuations, as if reality itself were boiling. This is the realm loop quantum gravity explores. Developed in the 1990s, it proposes that space is woven from minuscule loops, each loop representing the smallest possible unit of area or volume. Instead of a smooth sheet, space-time becomes a lattice of interconnected rings. Compress this lattice too far and it pushes back. There is a minimum size below which space cannot shrink, and because space cannot shrink to zero, a singularity can never form. Instead, when the density reaches that quantum limit, gravity reverses. The collapse slows, stops, and then rebounds outward. Physicists call this a quantum bounce. In cosmology, that bounce looks remarkably like a Big Bang, an explosion not from nothing but from a previous contraction, a universe collapsing in one direction then expanding in another. Einstein-Cartan theory adds another piece to this picture. In ordinary relativity, spacetime can bend but not twist. But real particles possess spin, a quantum property that carries angular momentum even when the particle is at rest. When matter becomes unimaginably dense, those spins interact with spacetime itself, creating torsion, a subtle twisting of the geometry. Torsion acts like an internal pressure. As the collapse intensifies, this pressure builds until it halts further compression. Nikodem Popławski used this mechanism to show that the interior of a black hole need not end at a singularity. As torsion grows, it forces the collapsing matter to rebound, creating an expanding region of spacetime on the other side of the horizon. From the outside, the black hole remains intact, but from the inside, an entirely new universe begins to unfold. This interpretation resolves problems that have troubled cosmology for decades. It explains why the early universe was astonishingly uniform. Before the bounce, all matter was compressed into the same collapsing region. It explains why spacetime expanded smoothly rather than chaotically. And it explains how our universe could begin not from nothing but from the death of something older. Seen from within, the rebound would look like a burst of space and energy exploding outward, the event we call the Big Bang. Seen from outside, it would look like a black hole quietly sitting in space, its interior forever hidden by its horizon. Two perspectives. One event, different realities depending on where you stand. This picture transforms the meaning of a black hole. Instead of cosmic dead ends, they become cosmic wombs, places where collapse gives way to creation. The fall into a black hole is the beginning of a timeline for the universe inside it. And the singularity we once feared is replaced by a bridge between worlds. In this view, the Big Bang is not the origin of all things. It is the moment when our universe took its first breath after a collapse in apparent reality. A transition rather than a beginning, a continuation rather than an absolute start. And if every black hole contains such a rebound, then the story of creation may repeat across the cosmos again and again, each horizon holding a new space-time waiting to emerge. Extraordinary ideas demand extraordinary evidence. If our universe truly emerged from the interior of a black hole, then the traces of that origin should still linger across the sky, woven into the light. We observe the galaxies we map, and the structure of space-time itself, and when we look closely, those traces begin to appear. The first clue comes from the oldest light in existence, the cosmic microwave background. It is the faint afterglow from when the universe was only a few 100,000 years old, a moment when light could finally travel freely through space. What makes this relic remarkable is how uniform it is. Across the entire sky, its temperature varies by only a tiny fraction. In the standard Big Bang model, distant regions should never have been in contact long enough to equalize. Yet they did. Inflation theory was created to explain this mystery. But if our universe began inside a collapsing region of a parent cosmos, then everything was already compressed together before the rebound. Uniformity is not an accident, it is inheritance. Another clue lies in the way galaxies rotate. Across vast stretches of the sky, astronomers have noticed a subtle imbalance. More galaxies spin one direction than the other. It is a faint signature, but statistically real. In a universe born from the interior of a rotating black hole, such an imprint is natural. The spin of the parent black hole would transfer angular momentum into the newborn spacetime, leaving a gentle twist written across billions of light years. Then came the James Webb Space Telescope, When Webb opened its golden mirrors and peered deeper into the past than any instrument before it, scientists expected to find small, fragile galaxies just beginning to form. Instead, they discovered giant, massive organized structures that appeared far too early. According to conventional models, there simply wasn't enough time for gravity to assemble them. But in a universe born from a rebound, the initial state is already dense, already structured. Early galaxies form quickly because they begin from a cosmos that was never truly empty. The holographic nature of black holes offers yet another hint. A black hole's information is stored not within its volume but on its surface. Its entropy scales with area not space. This idea led to the holographic principle, the concept that a three-dimensional world may arise from information encoded on a two-dimensional boundary. Our universe behaves in a strikingly similar way. The observable cosmos appears to contain only the information needed to describe events on its horizon. If our universe is the interior of a black hole, the geometry would require exactly that kind of encoding. Even direct observations of black holes support the picture. LIGO's detections of gravitational waves from merging black holes matched Einstein's predictions with stunning precision. The Event Horizon Telescope captured the shadow of a supermassive black hole, a perfect silhouette formed by the geometry surrounding its horizon. In both cases, the data align with the idea that horizons conceal whatever lies within. We see the boundary, never the singularity. The interior remains hidden not because nothing exists there, but because that interior is a space-time of its own. Taken alone, each clue has alternative explanations. Taken together, they begin to form a narrative, a universe that is smooth because it inherited its balance, a universe that carries a faint rotational memory, a universe where galaxies grow too quickly because their initial state was already compressed, a universe that behaves holographically as though its information is stored on a boundary, a universe where horizons behave like sealed surfaces around hidden interiors. None of this proves we live inside a black hole, but each observation bends the story in that direction, suggesting a cosmos that may be finite, curved, encoded, and born from something older. A cosmos shaped not in isolation but in continuation, the unfolding interior of an event horizon we can never cross. In the 1970s, something remarkable happened in theoretical physics. Stephen Hawking and Jacob Bekenstein discovered that black holes, the darkest objects in the universe, are not truly black. They have entropy, a measure of how much information they contain. But the surprise was not the entropy itself. It was how that entropy scaled. In everyday experience, information fills volume. A larger box holds more books. A bigger room contains more air. But a black hole breaks this rule. Its information content depends only on the surface area of its event horizon. Double the radius and the information increases by a factor of 4, not 8. Hawking and Bekenstein had uncovered a principle that seemed almost impossible. The boundary knows everything. This insight grew into what physicists now call the holographic principle. The idea that a region of space can be completely described by data encoded on its boundary, much like a hologram on a thin sheet of film can project a three-dimensional image. In this view, the interior of a black hole is not a void swallowing information. It is a projection of the information written on the horizon. 2 decades later, Juan Maldacena provided the most famous mathematical realization of this idea. His ADA-CFT correspondence revealed that a universe with gravity could be equivalent to a universe without gravity living on its boundary. Every event in the three-dimensional bulk has a mirror description in the two-dimensional surface. 2 different worlds, one shared physics, a perfect duality. For the first time, the holographic principle was not just a philosophical idea, it had a working model, a map between geometries, a demonstration that space gravity and even time could emerge from more fundamental information. And if black holes behave holographically, the natural question follows: what about the universe itself? When we look at the cosmos, we see a horizon the farthest distance light has reached since the Big Bang. That horizon acts like a boundary. It defines what we can observe and what forever lies beyond our reach. According to holographic reasoning, the entire history of our universe could be encoded on that surface. Every galaxy, every atom, every fluctuation of space-time, all projected inward, forming the three-dimensional reality we experience. This idea gained even more weight when we return to the possibility that our universe lies inside a black hole. The event horizon of that parent black hole would serve as the ultimate boundary storing the complete dataset of our cosmos. The physical world we inhabit, stars, planets, life, would be the interior projection of information imprinted on that surface. In other words, the holographic behavior of black holes is not an analogy. It is the blueprint for how our universe might function. Experiments have even begun to search for signs of holographic structure. Projects like the Holometer at Fermilab and the GEO 600 interferometer in Germany look for tiny holographic noise quantum jitters that would appear if space-time is built from discrete bits of information rather than a smooth continuum. So far the results remain inconclusive, but the search continues. Each improvement narrows the gap, pushing us closer to answering whether space itself is quantized. If the holographic principle is correct, the implications are profound. It means that the universe is not defined by the space it contains, but by the information at its boundary. It means that what we call reality may be an emergent phenomenon, a higher dimensional interior projected from a deeper layer of physics. And it means that if our universe was born inside a black hole, its entire structure would follow the same rules that govern black hole interiors. Holography ties the story together. The entropy law discovered in the 1970s, the quantum models of black hole interiors, the idea of a universe born from collapse, all of them point toward a vision of reality where information is fundamental and space-time emerges from the way that information is arranged. In this picture, the universe is not contained within space. It creates space, and if our cosmos is a holographic interior, then the edge of the observable universe is not just a limit of what we can see, it is the surface where our reality is written, the boundary from which every moment inside unfolds. When we look into the night sky, the universe feels endless. Galaxies stretch in every direction, and no matter how far we search, there is always more. It is easy to imagine that space goes on forever, but Einstein's equations tell a different story, one in which infinity is not required, and the shape of the universe may be far stranger than our senses suggest. In general relativity, space is flexible. It bends under the influence of matter and energy, just as a sheet of fabric bends beneath a heavy weight. Add enough mass and you do not just distort space locally, you curve the entire structure. A universe with high density can wrap back on itself, forming a closed geometry. In such a cosmos, you could travel in a straight line forever and eventually return to the point where you began, not because you looped around an edge, but because space itself is curved. Cosmologists have spent decades measuring that curvature with exquisite precision. They study the cosmic microwave background, the faint glow left from the early universe, to see how ancient light flows across the sky. In a perfectly flat universe, its patterns stretch out in predictable ways. In a curved universe, those patterns shift, becoming slightly larger or smaller, depending on the shape of space. The Planck satellite mapped that ancient light in extraordinary detail. The results suggested that the universe is almost perfectly flat, but almost is not the same as exact. A tiny positive curvature remains possible. In 2019, a reanalysis of the data even found hints that the universe might lean slightly toward a closed geometry. The evidence is not decisive, but the possibility remains open. Our universe could be finite, not infinite, yet boundless, looping back on itself far beyond our horizon. This idea aligns naturally with a universe born inside a black hole. The interior of a black hole is a region of intense positive curvature, a space folded inward by overwhelming gravity. If our cosmos occupies such an interior, its global geometry would echo those same curves. From within, the curvature would appear gentle, almost flat across billions of light years. but on scales we cannot observe much farther than any telescope can reach. Space may curve back on itself, just as the mathematics predicts. And the key is perspective. When you stand inside a curved space, the curve can be invisible. A person walking across Earth's surface sees a flat horizon, even though they move across a sphere. Only by travelling far enough would the arc become clear. Our universe may work the same way. We see flatness because our observable region is too small a window to reveal the fuller shape. If the cosmos is closed, then what appears infinite is simply the geometry of a vast self-contained bubble. A bubble expanding from within, shaped by the conditions of a black hole in a larger reality. The illusion of infinity comes from our vantage point, not from the true structure of space. And just as the inside of a black hole forces time to flow inward, the curvature of a closed universe links time and space in subtle ways. Expansion slows, geometry evolves. In the far future, the universe could even reverse its expansion, collapsing again into new black holes, each potentially seeding new universes in turn. In this view, the shape of our cosmos is not an accident. It is the echo of the geometry that gave birth to it, a faint reminder of the collapse that came before. When we measure curvature, we may be measuring the imprint of a parent universe. The curvature of a spacetime we can no longer see but still inhabit from within. So when astronomers say the universe appears flat, they are not declaring its true shape. They are describing only the part we can observe. Beyond that horizon, space may curve in ways we have yet to imagine, completing the sphere of a world born behind an event horizon. If that is true, then the cosmos is not infinite at all, but a closed, expanding interior. A curved island of space-time floating inside something far larger. When something falls into a black hole, it appears to vanish without a trace. Stars, planets, clouds of gas all cross the event horizon and seem to slip out of existence. From the outside, nothing remains except a dark sphere and the quiet pull of its gravity. For decades, this led physicists to believe that black holes were perfect destroyers, erasing not only matter, but the information that described it. Yet that idea struck at the heart of quantum mechanics, which insist that information can never be lost. The tension between these views became one of the greatest puzzles in modern physics. The information paradox. If a black hole eventually evaporates through Hawking radiation, and nothing escapes from inside, then where does the information go? If it disappears forever, then the laws of quantum theory fail. If it survives, it must be stored somewhere, but where could that be? The answer, strange as it sounds, lies on the surface of the event horizon itself. Hawking showed that black holes radiate energy due to quantum fluctuations near the horizon. Virtual particle pairs appear and vanish everywhere in empty space. If one of those particles falls inward while the other escapes, the escaping particle carries away a tiny bit of the black hole's mass. Over eons, this slow leak evaporates the black hole entirely, but the deeper insight came from Gerard 't Hooft and Leonard Susskind. They argued that the horizon encodes everything that ever falls in. Each particle that crosses the surface imprints a microscopic change in the geometry of the horizon. The interior we imagine the bottomless well is not where the information resides. The information lives at the boundary in patterns too small to see woven into the surface like the grain of a cosmic film. From this viewpoint, a black hole does not destroy information, it scrambles it. And as the black hole emits Hawking radiation, that scrambled information leaks back into the universe, buried in faint correlations between the emitted particles. The black hole becomes not a tomb but a memory device. A system that hides information only temporarily. Now imagine applying this principle to the universe itself. If our cosmos was born inside a black hole, then the event horizon of the parent black hole would serve as the boundary where all our information is stored. Every particle, every star, every moment of cosmic history would be encoded on that surface. What we experience as three-dimensional reality would be the interior projection of that encoded data unfolding in time from the inside. This interpretation turns the cosmic horizon into more than a limit of observation. It becomes the edge where our universe's information is written, just as the event horizon writes the information of a black hole's interior. The parallels grow stronger when we consider dark energy. As black holes evaporate, their horizons shrink. From the outside, this looks like a loss of mass. But from the inside, from the perspective of the universe within the changing horizon, could appear as an accelerated expansion of space. In other words, what we call dark energy might be the inside view of a horizon slowly evolving in a larger reality. Just as Hawking radiation drives the long-term fate of a black hole, the changing geometry beyond our cosmic horizon could drive the expansion within. This picture unites multiple mysteries at once. The information paradox, horizon entropy, holographic encoding, and cosmic acceleration become different facets of the same structure. A black hole hides its interior behind a horizon and stores all information on that horizon. A universe born inside a black hole does the same. We live in an environment where information never disappears. It merely moves, reshapes, and reappears in new forms. Everything we see in the cosmos, from the birth of stars to the scattering of galaxies, may be the unfolding shadow of information written at a boundary we can never cross. And the faint push of dark energy, the mysterious force stretching the universe, may be nothing more than the reflection of the horizon that surrounds us changing as the world beyond evolves. In this light, the universe is not a sealed box drifting in empty space. It is a dynamic interior illuminated by information stored at its outer edge. A world born from the physics of horizons and forever shaped by the surface that defines it. When we peer into deep space, we are not seeing distance, we are seeing time. Every photon that reaches our eyes has travelled across a universe that has been stretching, cooling, and evolving for billions of years. The farther we look, the older the light becomes, until eventually we hit a wall. A faint, glowing sphere of radiation that marks the moment when the cosmos first became transparent. This is the cosmic microwave background, the oldest photograph of the universe. Beyond that point, the past becomes unreachable, not because nothing exists there, but because light has not had enough time to cross the expanding space between us and those primordial regions. The boundary defined by that limit is called the cosmic horizon, the farthest edge of our observable reality. But if our universe lies inside a much larger structure, this horizon may be more than a simple limit. It may be the shadow of the event horizon of a parent black hole. From that perspective, everything we see, all galaxies, stars, and clusters, would exist within the interior of a vast self-contained space-time. Our entire cosmic history would be unfolding inside a bounded region, sealed off from any outside world by a surface we cannot cross. If that is true, we should expect subtle traces of the boundary imprinted on the sky. And when cosmologists study the CMB with exquisite detail, they find anomalies that don't fit neatly within the standard cosmological model. There is the cold spot, a region unusually large and faint. There is the axis of evil, a strange large-scale alignment in the temperature fluctuations. These patterns stretch across angles too immense to be caused by local physics. Some researchers propose that they may be echoes from the boundary conditions of a closed curved space. If our universe is indeed a finite interior, its horizon could leave fingerprints frozen in the oldest light we can see. Another hint comes from the accelerating expansion of the cosmos. Distant galaxies are not only receding, they are speeding up, driven by an unknown energy we call dark energy. In the standard model, this acceleration requires a mysterious form of vacuum pressure, but in the black hole inside model, it may have a different interpretation. If the event horizon of the parent black hole is slowly shrinking due to a process similar to Hawking radiation, the interior space-time would experience this change as accelerated expansion. What looks to us like dark energy could simply be the inside view of the horizon, evolving in the larger reality beyond our reach. Even the structure of observational limits itself aligns with this picture. Space is expanding faster than light can travel across it. Beyond roughly 46 billion light-years, no information will ever reach us, no matter how long we wait. This creates an observational cage not because of physical walls, but because of geometry. It is exactly what we would expect if we lived inside a bounded region of curved space-time defined by a horizon we cannot cross. From within such an interior, the universe appears enormous and nearly flat. But those impressions come from our limited vantage point. Just as a traveller on Earth sees a flat landscape despite standing on a sphere, we see a flat cosmos because our observable region is too small for the curvature to reveal itself. The true shape might be hidden beyond the horizon, folded into the geometry of the parent reality. If this interpretation is correct, the cosmic horizon is not merely the limit of what we can observe, it is the surface where our reality is written. It is the boundary that defines our universe, just as the event horizon defines the interior of the black hole. Every pattern in the night sky, every ripple in the CMB, every galaxy rushing away from us could be part of a deeper structure, the interior dynamics of a space-time we can never exit. And the expansion we witness, the quiet stretching of the cosmos, may be the inside view of a process playing out far beyond our own horizon, a whisper from the larger geometry that gave birth to our world. In the deepest view of physics, the universe may not flow from a single beginning to a single end. Instead, it may move through a continuous cycle of transformation, where creation and collapse are not opposite events but different stages of the same cosmic process. In such a picture, there is no absolute before or after. There is only the passing of information from one horizon to the next. Every black hole becomes part of that chain. When a star collapses and forms a horizon, information does not vanish, it reorganizes. Inside the new interior, space-time stretches, expands and evolves, giving rise to a universe with its own laws and geometry. The interior does not replace the exterior. It emerges from it like a branching path in an ever-growing network. From our perspective, sealed inside one of these interiors, the chain is invisible. We see only our own universe and mistake it for the entire structure. But the mathematics of gravity, quantum mechanics, and holography all suggest a larger architecture. Each event horizon could be a boundary in a vast cosmic lattice. Each collapse could ignite the birth of another cosmos, and each new universe may inherit pieces of the physics encoded in the horizon that came before. Imagine stepping outside this structure, not in space, but in a higher layer of existence where all horizons are visible at once. You would not see a single expanding bubble, but a web of them, each one glowing with its own history. Some would be young, filled with bright galaxies and new stars. Others would be ancient, fading towards silence. Black holes would appear as bridges between these worlds, points where one universe narrows into a surface and another begins to unfold. This network would stretch endlessly, not as a line, but as a fractal of creation, a geometry of expansion and collapse repeating across scales. The birth of a universe would be just one event in an eternal cascade, with no final origin and no ultimate edge. The cosmos would be self-generating each horizon, giving rise to another, each interior branching into its own reality. In this view, our universe sits somewhere in that infinite structure. It is young by cosmic standards, rich with star formation-heavy elements and the conditions for life. And within our own black holes, the process may already be continuing. Their interiors could be growing new regions of space-time, each one destined to evolve with laws influenced by the information we pass to them. Our geometry, our constants, our imprint on the cosmic chain. The flow of information becomes the heart of this continuity. Matter collapses into energy. Energy encodes itself as quantum states on a horizon. Those states define the initial conditions of a new expanding interior. The cycle repeats, not destroying the past, but transforming it into the blueprint for the future. Seen from this perspective, the question, where did everything begin, may not have an answer. The cosmos may have no first moment. Instead, existence evolves. Through an infinite sequence of transformations, each universe, a chapter in a book with no first page and no final line. Somewhere within this immense structure, a new universe is already forming. Perhaps it is taking shape inside one of the black holes at the heart of a distant galaxy. Perhaps it is still only a quantum seed suspended in the foam where space-time breaks down. But like ours, it will ignite. It will expand. It will create light stars and life. And one day beings within it may look into their night sky and wonder how everything began, unaware that they too are part of a cosmic lineage stretching far beyond their horizon. For most of human history, we believed we stood at the center of everything. The heavens revolved around us, the stars were lanterns hung for our eyes alone, and existence felt small enough to grasp. Then came the first great shift. Earth became a planet, the sun became a star, and our world shrank into a vast sea of galaxies. Each discovery pushed us farther from the imagined center of creation. Now physics invites us to accept an even deeper transformation, one more profound than anything that came before. It suggests that the universe we see, the one filled with galaxies and light, may itself be the interior of a larger structure, and within that interior we are not observers standing apart from the cosmos. We are patterns inside it, woven into the geometry that gives the universe its shape. Every atom in our bodies is a temporary form adopted by the fabric of space-time. The particles that make us are not separate from the forces that sculpt stars and bend light. They are expressions of the same underlying field. When you lift your hand, you're not moving inside space, you're reshaping space. When your brain forms a thought, that thought is a ripple of energy and information governed by the same rules that guide the evolution of the cosmos. Seen this way, the boundary between us and the universe begins to dissolve. We are not small creatures lost in a vast emptiness. We are localized features of the very fabric that composes reality. We are space-time organized for a brief moment into the form of a living being. Consciousness, in this interpretation, becomes the universe reflecting on itself, a temporary window through which the cosmos experiences its own structure. This idea grows even more striking when placed in the context of a universe born inside a black hole. If our world is an interior region of curved space-time, then every particle that forms our bodies, every neuron, every spark of thought, is part of the architecture of that interior. We are shaped by the same geometry that once defined the collapse of a star in a parent universe. Our physical laws are inherited constraints. Our constants are encoded values. Our existence is the unfolding of information seeded on a horizon we can never reach. In this picture, life is not an anomaly. It is an emergent expression of the universe's structure, a pattern complex enough to ask where the pattern came from. The curvature that defines our cosmos also defines us. The same equations that describe black holes and cosmic expansion describe the motion of molecules in our cells. There is no separation, only scale. Understanding this changes more than cosmology. It changes our sense of identity. We are not passive guests in a universe built elsewhere. We are intrinsic components of its geometry. Each heartbeat, each breath, each moment of awareness is part of the ongoing computation that space-time performs. We are the universe examining itself from within, a brief self-recognition in a cosmic process that stretches beyond horizons. And if the cosmos is a chain of interiors, each one giving birth to the next, then our existence is part of that continuity. The atoms in our bodies will one day collapse into new stars. Those stars may fall into black holes, and inside those black holes new universes may form, carrying forward echoes of the geometry we leave behind. In that sense, we are part of an eternal lineage, not descendants of ancient stars, but contributors to future worlds. Our physics, our structure, even the information encoded in our matter may shape the conditions of universes yet to be born. We are woven into the story at every level, past, present, and future. We once believed the universe was built for us. Then we learned we were small. Now physics offers a third revelation, that we were never separate at all. We are not outside observers. We are the fabric itself, momentarily aware of its own existence, living inside a reality far larger than we can see. What if space isn't something the universe possesses, but something it computes? Not a stage on which physics unfolds, but the result of deeper processes, patterns of information, arranging themselves into the geometry we experience as distance, shape, and motion. This question sits at the center of a profound shift in modern theoretical physics, one that reframes the very meaning of reality. Everything in the universe, from electrons to galaxies, can be described as information. In quantum mechanics, particles are not tiny billiard balls. They are wave functions, distributions of possibility. When two particles become entangled, their information merges, forming a single shared description. The universe becomes a web of relationships with nodes connected by invisible threads of correlation. Now imagine that these threads do more than link objects within space. Imagine they define space. Where entanglement is strong, the underlying nodes are close. Where it is weak, those nodes drift farther apart. In this view, distance is not measured with a ruler. It is measured by information. Geometry becomes a map of entanglement. This idea is more than poetic speculation. It is supported by concrete mathematics, most famously in the AD-SCFT correspondence. Maldaceno's breakthrough showed that a three-dimensional world with gravity could be fully equivalent to a two-dimensional quantum system living on its boundary. The entire interior, its distances, its curvature, even its flow of time emerges from correlations among quantum bits on the surface. Spacetime in this picture is not fundamental. It is built from entanglement. Mark van Ramsdonk pushed this further. He demonstrated that decreasing entanglement in a quantum system causes the corresponding spacetime to tear apart. Remove enough entanglement and the geometry fractures into disconnected regions. Restore the entanglement and the geometry knits itself back together. Space exists only because information binds it together. This interpretation dissolves the old divide between general relativity and quantum mechanics. Relativity describes how space bends. Quantum theory describes how information is structured. But if space is information, then the two are not competing frameworks. They're different perspectives on the same underlying process. At the smallest scales, the universe may resemble a quantum computation. Qubits flickering, entangling, and disentangling trillions of times per second. These qubits form patterns. The patterns form structure, and that structure becomes the geometry we move through. Wheeler captured this with a simple phrase: it from bit, everything that exists, it arises from binary choices from information itself. Modern physics refines this to it, from qubit expanding the idea into the quantum realm, where correlations, not just bits, encode the universe. In this light, gravity becomes an emergent phenomenon. It is not a force acting within space-time, but the result of information striving toward equilibrium. Mass curves space, because mass reorganizes the network of entanglement around it. Black holes warp space-time, not because they pull on it, but because they compress information to its maximum density. And this leads us to a remarkable realization. If space-time is generated from information, then the interior of a black hole, including our own universe, if we live inside one, is the emergent product of information encoded on its horizon. Everything we see is woven from correlations we cannot access. Every star, every atom, every breath is a pattern shaped by the information inscribed on that boundary. Space is not the container of reality. Information is. Space is simply its shadow. When astronomers mapped the positions of hundreds of thousands of galaxies, they expected to see randomness, scattered points in a vast cosmic sea. Instead, something astonishing emerged. The universe was not an empty expanse filled with isolated island of stars. It was a web, a luminous network stretching across billions of light years, with galaxies arranged along vast filaments of matter, separated by dark, silent voids. These filaments are not small. Some span hundreds of millions of light years longer than entire superclusters. Gas flows along them like rivers of light feeding galaxy clusters at their intersections. Gravity stretches them. Expansion pulls them. Over billions of years, they twist and thicken, forming the skeleton of the cosmos. Computer simulations such as the Millennium Run and Illustrious Project bring this evolution to life. They show how tiny fluctuations in the early universe grew, how matter gathered into strands, and how those strands assembled the cosmic architecture we see today. The simulations reveal a universe that behaves almost like a living organism, a structure that builds itself from simple rules, sculpted by the interplay between gravity expansion and time. Even more surprising is how familiar this structure looks. When scientists compared the distribution of galaxies in the cosmic web with high-resolution scans of the human brain, they found a striking similarity. Both systems, separated by 30 orders of magnitude in scale, share the same statistical patterns. Nodes connect through filaments. Clusters form where connections strengthen. Voids appear where connections fade. The universe and the brain both seem to follow a natural blueprint for complexity. This resemblance isn't superficial. In the brain, electrical signals travel along networks of neurons, strengthening pathways that carry information. In the universe, matter flows along gravitational channels shaped by dark matter, an invisible scaffolding that defines the geometry through which galaxies evolve. Dark matter outlines the cosmic web the way bones outline the structure of a body. We cannot see it directly, but gravitational lensing reveals its shape as it bends the light of distant galaxies, sketching an invisible map beneath the luminous one. The deeper mystery comes from the idea that the cosmic web may not only organize matter, it may also organize information. If space itself emerges from the geometry of entanglement, as theories like it from qubit suggest, then the web could be the large-scale echo of a microscopic information network. Every filament, every cluster, every void might reflect the subtle distribution of correlations that define the fabric of space-time at the smallest scales. In this interpretation, the universe behaves like a vast circuit. Galaxies are nodes, filaments are channels, dark matter is the wiring beneath it all, and the flow of energy and information through this system shapes the evolution of cosmic structure. The web becomes a map not only of matter, but of the logic that governs the universe. And if our universe was born inside a black hole, this pattern takes on a deeper meaning. The filaments could be the macroscopic imprint of the information encoded on the parent horizon, a scaled-up expression of the entanglement network that generated our space-time. Just as a fractal repeats its pattern at different scales, each universe in a chain of universes might develop its own web, echoing the structure of the one before it. Picture this: a black hole collapses in a parent universe encoding information on its event horizon. Inside that horizon, a new universe forms and expands. Its space-time is shaped by the information it inherited. That information blossoms into structure, and billions of years later that structure appears to us as the cosmic web. The pattern repeats: collapse, encoding, rebirth, structure, and eventually collapse again. A fractal of universes, each one carrying the imprint of the last, each one growing its own web of light and darkness, each one passing its geometry forward through the physics of horizons. In that sense, the cosmic web is more than the architecture of our universe. It is a message, a signature, a reminder that structure emerges from deeper patterns, patterns older than our cosmos, inherited across boundaries we cannot cross. If our universe truly emerged from the interior of a black hole, then everything we know, every atom, every star, every breath we take is part of a story much larger than the one we can see. We are not living in a void that came from nothing. We are living inside a continuation, a chapter in an endless chain of creation and collapse, written across horizons we can never cross. The event horizon that surrounds our universe may hold the complete quantum record of everything that has ever happened here. Every structure, every fluctuation, every thought leaves a microscopic trace on that distant boundary. From outside, those traces would form the initial conditions of our cosmos. From inside, they become the fabric of space, the march of time, and the evolution of everything we observe. We often imagine the universe as something external, a vast stage on which we appear, act, and eventually vanish. But physics paints a different picture. We are not visitors inside this cosmos. We are expressions of it. The atoms in our bodies were forged in ancient stars. The elements in our bones once drifted through interstellar clouds. The energy that allows us to think and feel comes from processes that began long before Earth existed. We are not separate from the universe. We are one of its many forms, and if space itself emerges from information, then consciousness. The ability to reflect, to wonder, to ask questions about our place in reality becomes a universe examining itself. Every scientific discovery, every moment of clarity is a small window through which the cosmos becomes aware of its own structure. Our curiosity is not an accident. It is a feature of the geometry that created us. This perspective also changes the way we think about beginnings. The Big Bang may not have been the start of everything. It may have been the transition from a collapsing world in a parent universe into the expanding world we inhabit now. And when our universe grows old, when its stars fade and its matter falls into black holes, new universes may emerge inside those depths, carrying forward the information that once shaped ours. A chain with no first link, a story with no opening line, a process that repeats across scales we cannot imagine. In this view, the cosmos is a living network of horizons. Each horizon marks the end of one reality and the birth of another. Each universe inherits the encoded patterns of the one that came before its geometry, its constants, its potential for complexity. And through that complexity, life appears. Life organizes matter. Matter organizes information. Information organizes spacetime. And spacetime organizes universes. It is a cycle that ties everything together, from the smallest quantum events to the largest cosmic structures. We may never see beyond our horizon. We may never observe the parent universe directly, but we do not need to. The clues are already written in the sky, in the cosmic microwave background, in the structure of galaxies, in the behavior of black holes, in the unfolding of space-time itself. They point to a universe that sprang from something older, and to a future where the pattern continues. Perhaps the greatest revelation is this: we are not insignificant. We are not alone in a cold, indifferent void. We are part of a cosmic lineage, a chain of realities stretching far beyond our horizon. And somewhere in the depths of a distant black hole, another universe may be forming right now. A universe that will ignite, expand, grow its own stars, its own galaxies, its own life. A universe that will look into its night sky one day, searching for answers just as we do now. We are the universe becoming aware of itself, a momentary spark in an eternal process. And the story continues. Since the beginning of human memory, we have lifted our eyes to the night sky and wondered where it ends. The darkness seems endless. The stars appear to stretch forever. And yet science tells us something far stranger than an infinite sky. The universe has a limit, not a wall, not an edge we could touch, but a boundary defined by time itself. When we look into space, we are not seeing distance. We are seeing history. Light does not arrive instantly. It travels. It carries memories of where it came from, crossing emptiness for billions of years before reaching our eyes. Each additional step into the darkness is a step backward in time. A galaxy 1,000,000 light-years away shows us a million-year-old picture. A galaxy 10 billion light-years away reveals an image carved when the universe was young. But this time-travelling vision has a hard stop. The universe has existed for only about 13.8 billion years. Light has had only that long to reach us. No matter how powerful our telescopes become, we cannot see farther than the distance light has been able to travel since the birth of the cosmos. That limit draws a sphere around us, the observable universe. Everything inside it is part of our cosmic horizon. Everything beyond it remains hidden. This boundary is not physical. If you could teleport past it, you would not hit a wall or a curtain of darkness. Space continues freely. Galaxies exist beyond our sight, drifting through regions we will never observe. The limitation is not in the universe. The limitation is in us, in the finite speed of light and the finite age of everything around us. For thousands of years, ancient stargazers imagined the heavens as a dome above the Earth. Today we understand far more, yet the question that haunted them is still with us. Where does the universe end? What lies beyond the farthest star we can detect? If the universe is larger than the part we can see, how much larger is it? And does something exist on the other side, or does that phrase lose meaning entirely once we leave the realm of what light can reveal? Astronomers use the term cosmic horizon for this boundary. It is like standing in the middle of a vast fog. You can see only as far as the fog allows, even though the world continues beyond your view. Our horizon is defined not by mist, but by time. The early universe was once so hot and dense that light could not move freely. Only after it cooled did photons begin their long journey across the growing cosmos. The farthest light that has reached us comes from a time when the universe was still shrouded in glowing plasma. A faint ancient remnant we now detect as the cosmic microwave background. Beyond that horizon lies a region we cannot touch, probe, or map. It is not dark because nothing is there. It is dark because nothing from that realm has ever had time to visit us. The universe may continue endlessly. It may curve back on itself. It may contain structures, galaxies, or even entire realms forever hidden from our perception. But from where we stand, all we can see is the interior of a cosmic bubble carved out by the speed of light. This is one of the deepest mysteries of modern cosmology. We can measure the universe. We can chart its history. We can watch its expansion unfold. But when we ask what lies beyond the edge of what we can see, our tools fail us. Physics tells us why the horizon exists, but not what lies outside it. And so the ancient question remains more powerful than ever. What lies on the other side of the universe? A question defined not by the stars we see, but by the light that has yet to reach us and may never arrive. Light is the fastest thing in the universe, yet even it cannot reveal everything. It has a speeder limit, a maximum pace at which information can travel. And because the universe has only existed for about 13.8 billion years, light has had only that long to reach us. This single fact creates the most important boundary in cosmology. The particle horizon. Imagine the universe as a vast ocean of darkness. Every star, every galaxy, every flicker of radiation is like a distant lighthouse casting beams across the waves. But no matter how bright those lighthouses are, their signals need time to arrive. If a galaxy is so far away that its light would take longer than the age of the universe to reach us, then we simply cannot see it. Its light is still on the way, crossing unimaginable distances through expanding space, but it has not arrived and may never arrive. This is why the observable universe is not the same as the entire universe. The observable universe is just the portion whose light has had time to reach our position in space. It forms a sphere around us centered not on Earth, but on every observer wherever they stand. Every civilization on every world would see its own version of this bubble. It is a horizon carved by time, not shaped by any physical structure. From within this bubble we see billions of galaxies scattered like frozen moments in history. But beyond its boundary there could be trillions more. Space does not stop at our horizon. It stretches far beyond, perhaps endlessly. The only thing that stops is the flow of information. The universe outside our horizon is not dark because nothing exists there. It is dark because light from those regions has not had enough time to reach us. And because space is expanding, some of it never will. This creates a strange situation. Right now, galaxies exist beyond the reach of our perception. They are real. They have stars, planets, perhaps even life. But from our point of view, they are hidden behind a curtain of time. Their light will forever remain beyond our grasp, like a message sent too late to ever arrive. To visualize this, imagine standing in a landscape covered in thick morning fog. You can see a small circle around you, perhaps a few meters across. But the world does not end there. It continues in every direction, full of forests, mountains, and distant places you cannot see. The fact that you cannot observe them does not make them disappear. The limitation belongs to your eyes, not the landscape. Our cosmic horizon works the same way. It marks the limit of the known, not the limit of the real. And this leads to a profound question. If the horizon hides most of the universe from us, then what lies beyond it? Is it more of the same endless galaxies and clusters repeating into the darkness? Or does something different wait on the far side of the observable world? We do not know, but everything we have learned so far points to a universe far larger, far stranger, and far more mysterious than the bubble of light we inhabit. The horizon does not enclose the universe. It encloses our understanding. The universe is not just expanding, it is expanding faster with every passing moment. Galaxies are carried outward on a tide of stretching space, and the farther they are from us, the faster that tide pulls them away. At great enough distances, space expands so quickly that even light travelling at its absolute limit cannot bridge the growing gap. No matter how long we wait, no matter how sensitive our telescopes become, the signals from those regions will never reach us. This defines the cosmic event horizon, the boundary that separates the part of the universe we can one day observe from the part we never will. It is not a wall. It is not a structure embedded in space. It is simply the distance beyond which the expansion of the universe outruns the speed of light. Anything crossing that threshold is carried away faster than the information can approach. To understand this, imagine standing on a shoreline as the tide pulls the ocean away from you. Boats drift out to sea, moving with the water rather than against it. They are not accelerating under their own power. The ocean itself is carrying them. In the same way, galaxies are not racing through space faster than light. Space itself is expanding beneath them like a rising wave, stretching the distance between us. Every galaxy beyond a certain radius is caught in this outward rush. Light it emits today will never arrive here. Not in a billion years. Not in a trillion. The expanding fabric of space will always pull it away faster than the light can push forward. This makes the event horizon fundamentally different from the particle horizon. The particle horizon tells us how far back into time we can see. The event horizon tells us how far into the future we can see. They are two boundaries shaped by two different constraints, one set by the past, the other by the future, and the event horizon carries an unsettling implication. Many of the galaxies we see today are already beyond it. Their light left them billions of years ago when they were still within reach. But since then, space has expanded so dramatically that they now drift into the unreachable zone. Their future light will never reach us, even though their ancient light still paints our sky. We are watching ghosts, images from a time long gone, snapshots from galaxies whose modern forms we will never witness. In the far future, the night sky will grow emptier. One by one, distant galaxies will fade away, not by dimming, not by dying, but by being carried across the event horizon. The cosmic landscape we observe today is temporarily shaped by the interplay between light and expansion at this moment in cosmic history. This phenomenon also reshapes how we think about what lies beyond our observational bubble. Beyond the event horizon, the universe does not merely remain unseen. It becomes fundamentally unknowable. Regions deeper in space may contain structures, clusters, even entire cosmic patterns we will never interact with no matter how long our civilization survives. The observable universe is therefore not just a limit of technology or perspective, it is a limit of causality, a boundary defined by the fact that some places in the universe are receding from us more quickly than the universe allows information to travel. Beyond that horizon lies a realm forever disconnected from our future, a place whose light can never reach our world, whose events can never influence us, and whose existence we must infer through theory alone. A reminder that the universe is not merely vast, it is divided by horizons we can never cross. When people imagine the end of the universe, they often picture a frontier, a final wall, a curtain of stars, or a cliff where space simply stops. It is a deeply human image shaped by landscapes we grew up with. Every ocean has a shore, every map has an edge, every journey eventually reaches a boundary. But the universe does not resemble the world that taught us those intuitions. There is no cosmic coastline, no wall, no outer shell. The universe does not sit inside anything else. It is not a bubble suspended in a larger realm. It is the framework itself, the totality of space and time, the geometry within which everything happens. Asking what lies outside the universe is like asking what lies north of the North Pole. The question feels meaningful until you examine it closely. North of the North Pole is not a location that exists. It is a direction that stops making sense once you reach the point that defines it. In the same way outside the universe is not aware. It is not a place separated from us by distance. It is a concept that dissolves when applied to a structure that contains all possible locations. If the universe had an edge, a literal border, then that border would itself be a region of space. It would have a location, it would be somewhere, and therefore it would be part of the universe. The very idea of an edge contradicts its own premise. What misleads us is visualization. We imagine the universe from the outside as if floating above it, gazing upon it like a glowing sphere in an endless void. But that image sneaks in an assumption that there is an outside viewpoint. There isn't. There can't be. To stand outside the universe, you would need a place to stand and a time in which to stand there. Yet both place and time are contained within the universe itself. Instead, the universe is more like the surface of the Earth, but in a deeper, higher dimensional sense. The surface has no edge yet, it is finite. You can walk endlessly and never fall off. Similarly, space can curve or wrap or extend without ever requiring a boundary. The universe can be finite without having a border or infinite without needing a container. The absence of an edge is not an emptiness. It is a feature of how space itself works. General relativity describes the universe not as a thing inside space, but as the shape of space. Space is not a stage. It is part of the cast. Its geometry is woven into matter, energy, and time itself. So when we ask what lies beyond the universe, the answer is not darkness or nothingness. The answer is simply, the question does not point in any direction reality can follow. The universe does not end the way a road ends. It ends the way a definition ends at the limits of what the words can describe. And yet this does not diminish the mystery. It deepens it, because if there is no outside, no edge to cross, then what we truly confront is something far more profound. A horizon not defined by space, but by understanding. The universe does not hide a border from us. It removes the very idea of a border, leaving us with the reality that has no outside, only depths we have yet to fathom. When we look out into the universe, we discover something remarkable. No matter which direction we choose, the cosmos looks nearly the same. The large-scale structure galaxies, clusters, filaments, and voids spreads out with a quiet uniformity, as if the universe were drawn with a steady hand across unimaginable distances. The faint afterglow of the Big Bang, the cosmic microwave background shows almost perfect smoothness, interrupted only by tiny ripples that seeded the formation of galaxies. This uniformity reveals something profound. It suggests that our observable universe is not a special place, not the center of anything, not a cosmic island with unique properties. It is simply one patch in a much larger expanse, an ordinary region of an extraordinary whole. And measurements of cosmic geometry strengthen this idea. When astronomers map the shape of space using the positions of galaxies and the patterns etched into the CMB, they find that the universe appears to be flat, not curved like the surface of a sphere, not warped like a saddle, but flat to astonishing precision. A flat universe does not require a boundary. It does not curl back on itself. It does not close like a loop. A flat universe can continue forever. If this is true, then the universe might be infinite, stretching beyond our horizon, beyond our imagination, beyond any measurement we could ever attempt. The observable universe would then be nothing more than a tiny window carved out by the speed of light, an infinitesimal bubble floating inside an endless cosmic plane. Picture a person standing in the middle of a great desert. The horizon forms a circle around them, but the desert does not end there. It extends far beyond what their eyes can see. In the same way, our cosmic horizon wraps around us like a circle of light, but the universe continues into distances beyond all sight. If we could move faster than light, or wait beyond eternity, or somehow step outside the limits of time, we might discover that the pattern of galaxies repeats endlessly. Cluster after cluster, filament after filament spreading without edge or boundary. Perhaps the structure we observe here, this web of matter and voids, is only one thread in a tapestry that spans infinity. This raises a remarkable possibility. Most of the universe lies forever outside our view. Not a little more, not twice as much, but perhaps an infinite amount more. The galaxies we observe, the ones we study, measure and catalogue, would then form a vanishingly small part of what exists. A grain of sand on a cosmic shore we will never reach. The implications are staggering. If the universe is infinite, there are infinite galaxies, infinite stars, infinite worlds, infinite variations of cosmic history unfolding beyond our horizon. In an infinite universe, even the rarest events occur countless times. And yet, for all this grandeur, infinity does not change the reality we face. We will never see beyond our bubble. Light from those unreachable regions will never reach us. The expansion of space prevents any information from crossing the gulf. Infinity may exist, but it remains forever hidden. This is one possible answer to what lies beyond the observable universe. Not mystery, not other realms, not alternate physics, but simply more universe, more of the same vast structure we see here stretching onward without limit. If the universe is infinite, then our observable world is not the full picture. It is only the part illuminated by light that has had time to reach us. A single frame of an endless film, and beyond that frame the story continues across distances we cannot begin to fathom. Not every path beyond our horizon leads to infinity. There is another possibility, one far stranger yet entirely allowed by the laws of physics. The universe may be finite in size and still have no edge at all. To understand this, imagine shrinking yourself down and walking across the surface of the Earth. From your perspective, the ground stretches smoothly in every direction. You can walk for a lifetime and never fall off a cliff labelled end of the world. The Earth's surface has no boundary, and yet it is not infinite. It wraps back on itself in a continuous curve. Now extend this idea into 3 dimensions. Space itself could behave like the surface of a sphere behaves in 2. You could travel in a perfectly straight line, never turning, never changing direction, and after an inconceivably long journey, eventually return to the point where you began. Not because you curved, but because space curved around you. This is what physicists mean by a finite but unbounded universe. It is a cosmos with volume, shape and structure, yet without a border. No outer wall, no final frontier, no place where space stops and something else begins. Instead, space loops, folds or wraps through higher dimensional geometry, forming a seamless manifold with no edges to find. We would never notice such curvature in our daily lives. The observable universe is far too small a region for these global properties to reveal themselves, just as a person standing in a field cannot sense the curvature of the Earth. Our telescopes cannot easily sense the curvature of the cosmos. Over small distances, a sphere feels flat. Over small distances, even a curved universe feels infinite. But physics offers clues. If the universe were finite in this way, light could travel around it. A photon emitted in one direction could give an enough time loop through space and approach us from behind. In principle, we could see multiple images of the same galaxy, a cosmic hall of mirrors formed not by reflection but by topology. Some scientists search the cosmic microwave background for repeated patterns for matched circles or distortions that might hint at a wrapped universe. So far, no conclusive evidence has appeared. But the absence of proof is not proof of absence. The universe could simply be far larger than the region we can see, and its curvature too gentle for us to detect. A finite but unbounded cosmos also reshapes our intuition. It tells us that size is not the same as having an edge. A universe can be limited and limitless at the same time, limited in volume, limitless in exploration. You could travel forever without encountering a border, not because space is infinite, but because space offers no place to stop. This idea dissolves one of the oldest images in human imagination. The universe as a container. Instead, the universe becomes a structure, a shape, a geometry without outside or inside. There is no beyond in the traditional sense. The universe includes itself, and if this is the true nature of reality, then what lies past our horizon may not be distant worlds extending endlessly outward. It may be regions of the same cosmos curved so subtly that we misinterpret them as separate when in fact they are threads in a loop far greater than we can perceive. In a finite but unbounded universe, the horizon is not the beginning of infinity. It is simply the limit of visibility within a cosmic shape too vast to grasp. To understand what might lie beyond our cosmic horizon, we first need to understand a deeper question. What is the shape of the universe itself? In everyday life, space feels flat. Lines seem straight. Distances behave predictably. But general relativity reveals a different truth. Space is flexible. It bends. It stretches. It curves around matter and energy like a sheet of fabric pulled into shape by invisible hands. The more mass or energy a region contains, the more dramatically the fabric warps. If we could step far enough back, far beyond any possible vantage point, we might see the geometry of the entire universe, the way one might see the curvature of the Earth from orbit. And the possibilities are extraordinary. One option is a closed universe curved like the surface of a sphere but in 3 dimensions. Travel far enough in a straight line and you would eventually return to your starting point, not because you turned, but because space itself folded around you. Such a universe is finite in volume yet without an edge. Another option is an open universe curved like a saddle. Space would expand forever, diverging as you travel outward. Distances would stretch faster than intuition expects. Geometry would behave subtly differently and parallel lines would drift apart. And then there is the most delicate possibility of all, a flat universe. Neither curved like a sphere nor bent like a saddle, but balanced with exquisite precision. A universe where the large-scale geometry is so even, so finely poised, that space behaves as though it stretches in perfectly straight directions across unimaginable distances. This is the universe we appear to live in. Measurements of the cosmic microwave background show that space is flat to within a fraction of a percent. It is astonishingly precise, like balancing a pencil on its tip for billions of years without it ever falling. Such precision demands explanation, and it carries profound meaning for what lies beyond our view. A flat universe does not curl back on itself, nor does it twist outward with accelerating curvature. Instead, it suggests vastness, immense scale, a cosmos so large that any curvature it possesses is too subtle for us to detect within our tiny observable patch. Imagine standing on the surface of an immense world, a planet so huge that even after travelling for a lifetime, the horizon still looks perfectly straight. The curvature is there, but it hides behind scale. In the same way, our universe may be curved, but across distances far greater than the region illuminated by light. Flatness also tells us something else. The universe's energy density is very close to a critical value, a knife-edge balance that determines cosmic destiny. Too much energy and space collapses inward. Too little and it expands apart with growing curvature, but at the critical point space expands steadily, maintaining a geometry that appears almost perfectly uniform. This delicate balance shapes everything we see. The distribution of galaxies, the temperature of the CMB, the formation of cosmic structure, the size of our horizon, and it hints that the universe we observe is only a tiny portion of a structure far larger than we can imagine. If the universe is truly flat, then whatever lies beyond our observational bubble likely follows the same rules, the same geometry, the same vast network of matter and voids. The cosmos may continue outward in all directions following the same straight lines we observe here, But if the flatness is only an illusion created by our limited perspective, if space does curve on scales beyond our reach, then the universe might have a global shape we cannot detect, a hidden geometry waiting just beyond our cosmic horizon. In either case, the curvature of space is not merely a mathematical detail. It is a message. It tells us that the universe has a structure, a shape, a global identity that extends beyond the small region we're able to observe. We live within a fragment of a far larger form, a local piece of a geometry that may stretch without edge curve, without boundary or wrap, through dimensions we cannot perceive. To understand what lies beyond our horizon, we must understand the shape of everything. And the shape of everything is written faintly but unmistakably in the way space bends. The expansion of the universe is one of the most counterintuitive ideas in science. We imagine galaxies drifting through space like boats sailing across a vast ocean. But this picture is wrong. In reality, the galaxies are not moving through space. Space itself is growing, stretching like an invisible fabric pulled from every direction at once. If you could watch the universe in fast motion, you would not see galaxies racing outward under their own power. You would see the distances between them swelling, as if the cosmic stage were slowly widening beneath their feet. Every moment more space exists than the moment before. Every second the universe becomes larger simply because the fabric of reality is expanding. This expansion has no center, no preferred direction, no origin point you could travel toward or away from. It is everywhere at once, the same in all directions, the same from every vantage point. If you were standing in a distant galaxy 10 billion light-years from here, you would see exactly the same thing we see. The galaxies around you drifting away in every direction. The most famous analogy for this is the surface of a balloon being inflated. Imagine drawing tiny dots on the balloon. As it expands, each dot moves away from all the others, even though none of them are sliding across the surface. The surface itself is growing, carrying each dot with it, and from the perspective of any one dot it looks like all the others are retreating. But even this image is limited. The universe is not expanding into anything. There is no external space surrounding it, no outer void waiting to be filled. When the balloon analogy tempts us to picture the universe expanding into some larger realm, we must resist the intuition. The expansion takes place within the universe, not outward into something else. The more space stretches, the more dramatic the effect becomes at large scales. Nearby galaxies remain bound to us by gravity, locked in a slow dance that prevents them from drifting away. But galaxies far enough from our own are swept into the current of expansion. The farther they are, the faster that current appears to pull them. This is why every observer sees themselves as the center of expansion, not because they are special, but because expansion is uniform. It acts everywhere on every region of space at every moment in time. There is no privileged point from which the expansion radiates. The fabric stretches equally throughout the cosmos. This universal stretching is what gives rise to the cosmic redshift, the lengthening of light waves as they travel through expanding space. The farther a galaxy is, the more its light is stretched and the redder it appears. By measuring this redshift, astronomers can trace how the universe has grown over billions of years. The expansion also shapes our horizons. Because space grows while light travels through it, distant galaxies drift away faster than light can compensate. Photons must cross an ever-growing gulf, and for sufficiently distant objects, that gulf widens faster than photons can advance. Their light never arrives. The universe hides them behind a moving boundary defined by the expansion itself. This means that the visible cosmos is not only limited by the age of the universe, but by the rate at which space expands. The faster the expansion, the more of reality slips beyond our reach. In a universe that stretches forever, the horizon does not stand still. It moves. It carries galaxies out of sight one after another like lanterns disappearing into an endless fog. And yet despite this grand motion, everything feels still from our perspective. The Earth does not drift. The stars in our galaxy do not fly apart. Gravity binds our cosmic neighborhood together while the rest of the universe is carried away on a tide we can sense only by watching distant galaxies recede. The expansion gives us a profound answer to our question. What lies beyond what we can see? It tells us that what lies beyond may not be unreachable because it is too far, but because the space between us is growing faster than light can cross it. The universe is not expanding into something else. It is expanding from within, carrying the unknown with it. Beyond our horizon, the expansion continues, carrying galaxies deeper into the dark, carrying secrets we will never witness, carrying the rest of the universe forever out of reach. When astronomers began charting the universe, they expected a kind of cosmic randomness, galaxies scattered like grains of sand blown across an endless beach. What they discovered instead was breathtaking order. The universe, on its largest scales, is woven into a structure so vast and intricate that it dwarfs every galaxy within it. This structure is known as the cosmic web. It stretches across billions of light years, a titanic lattice of filaments and nodes glowing with the light of countless galaxies. Each filament is a river of matter, hundreds of millions of light years long, carrying gas stars and dark matter through the void. Where these rivers intersect, they form superclusters, cities of galaxies bound together by gravity, and between the filaments lie immense cosmic voids, empty regions so large that entire galaxy clusters could drift through them without ever meeting another. This web was not carved by hand or guided by intention. It emerged from something simple, tiny fluctuations in the density of the early universe. Where matter was slightly denser, gravity pulled more matter in. Where it was slightly thinner, matter drifted away. Over billions of years, these subtle contrasts grew into the grand architecture we see today, an interconnected network spanning the observable cosmos. Computer simulations reveal the process in haunting detail. In projects like the Millennium Run and Illustri's cosmologists watched virtual universes evolve from mere wisps of density into sprawling webs of galaxies. The simulation begins with a faint mist uniform quiet, almost featureless. Then gravity begins to tug. Streams of matter form, lines sharpen, nodes brighten, and slowly the web emerges like frost growing across a window pane. Our own Milky Way lives inside one of these filaments, surrounded by neighbours bound together in a small corner of a vast cosmic city. We orbit a point on a structure so huge that even travelling at the speed of light, it would take us millions of years to reach the next major intersection. The scale is beyond comprehension. A single filament can stretch so far that if the Milky Way were reduced to a grain of sand, the filament would be longer than a continent. The voids between them are even larger oceans of nothingness, silent and cold, where galaxies are rare and loneliness becomes a physical place. This is the part of the universe we can see, a fraction, a sliver, a tiny window cut into a structure that almost certainly extends far beyond our horizon. Because if the cosmic web looks this way here, there's every reason to believe it looks the same out there, far beyond the boundary defined by the speed of light. The web does not end at the edge of our observation. It simply disappears behind the curtain of distance and time. And the implications are profound. It means that the grand structure we witness, this network of galaxies and voids, may only be one thread in a tapestry stretching across spaces we will never reach. Each filament may continue onward into realms whose light has not yet arrived. Each void may open into regions forever hidden from view. Our observable universe may be nothing more than a local patch of a cosmic web so immense that even eternity would not reveal it all. The cosmic web gives us a rare glimpse of the universe's true nature. It is not chaos. It is structure. It is pattern. It is the frozen memory of gravity sculpting matter over billions of years. And if this is what the universe looks like within our limited horizon, then beyond that horizon, the web may continue without end, stretching into darkness we can sense but never fully see. When we gaze deep into the universe, we're not looking into distance, we're peering back through time. Every additional billion light years we see represents a billion years of cosmic history rewinding one frame at a time. But this journey into the past has a final stop, a point beyond which even light cannot guide us. Roughly 380,000 years after the Big Bang, the universe underwent a transformation. Before that moment, it was a furnace of charged particles, electrons, protons, and radiation, swirling in a cosmic fog so dense that photons could not travel freely. Light was trapped, scattered endlessly, unable to move more than a fraction of a millimeter before being thrown off course again. The early universe was bright, but its brightness was locked inside an opaque storm of matter and energy. Then something changed. The universe cooled, electrons and protons combined to form neutral atoms, and for the first time light could slip through the cosmic fog. That ancient light has been travelling ever since. It has crossed the entire age of the universe, stretched into microwaves by the expansion of space, and now washes over Earth as the cosmic microwave background, the oldest light in the cosmos. It is the universe's baby picture, a portrait taken when the cosmos was less than 400,000 years old. When we look at the CMB, we are staring at a wall of time, not because something lies behind it blocking our view, but because light from earlier eras has never reached us. The universe before that moment is hidden behind a veil not of matter but of physics. Photons from that era could not escape. They could not begin their journey. They simply did not exist as messengers capable of carrying information across the cosmos. In this sense, the CMB forms the inner surface of our observable horizon. Everything we can see lies on our side of that surface. Everything earlier lies beyond it. The CMB is not the edge of the universe, it is the edge of visibility. A spherical shell of ancient radiation surrounding us from every direction, and the picture it gives us is astonishing. Across the entire sky, the CMB is almost perfectly uniform, the same temperature to 1 part in 100,000. Those tiny ripples, faint and delicate, represent the seeds of every galaxy that now fills the universe. The entire cosmic web we observe began as small wrinkles imprinted on this primordial backdrop, but the uniformity also tells us something else. The region of the universe we can see is only a tiny piece of something much larger. The CMB looks the same from all sides, suggesting that the universe beyond our view may follow the same pattern, a vast expanse of matter and energy that stretches far beyond our cosmic horizon. And yet no amount of improvement in technology will ever let us see past the CMB with ordinary light. It is a permanent limit, a curtain tied to the very physics of the early universe. To glimpse earlier times, we must rely on different messengers. Gravitational waves, neutrinos, or theoretical constructs that reach beyond the limits of electromagnetism. The CMB does not show us what lies beyond the universe. It shows us what lies at the farthest edge of our sight, a shimmering wall of ancient light marking the boundary between what the universe reveals and what it keeps forever hidden. The cosmic microwave background is often described as the farthest thing we can see, but that phrasing hides a deeper truth. The CMB is not far away in space. It is far away in time, and what lies beyond it is not the edge of the universe, but an era we can never witness with light. Before the universe became transparent, it was a wildly different place. A churning ocean of plasma so dense that photons could not travel more than a heartbeat before crashing into an electron and scattering again. The cosmos glowed with unimaginable brilliance, yet that brilliance could not escape. It was trapped within the primordial fog, folded into the chaotic dance of matter and radiation. If we could step through the CMB, if we could peel back that thin shell of ancient light, we would find ourselves inside a universe blazing with heat, noise, and motion. Atoms did not yet exist. Neutral matter had not formed. Everything was ionized, torn apart by temperatures so extreme that even the fundamental forces behaved differently. It was a realm shaped not by stars and galaxies, but by the raw physics of creation. This hidden universe is not empty, It is filled with clues about the origins of everything we see today. Density waves rippling through the plasma, turbulence sculpted by gravity, the faint heartbeat of sound waves echoing through the early cosmos patterns we can still detect frozen in the CMB's subtle variations. These ripples formed the blueprint for the cosmic web that would emerge billions of years later. Yet for all its significance, this era is forever beyond our vision. Light cannot carry us there. Photons did not survive that journey. The universe before the CMB is a chapter written in a language light cannot speak, but other messengers might. Neutrinos forged in the first seconds after the Big Bang still drift through the cosmos in unimaginable numbers. Gravitational waves, ripples in spacetime itself may carry information from time so early that even the formation of atoms lies in their distant future. These signals are faint, buried beneath the noise of the modern universe, but they offer a whisper of what lies beyond the reach of light. And this brings us to the most tantalizing possibility of all. When we ask what lies beyond the CMB, we are not only asking about a hotter, denser universe, we are asking about the moment before structure existed, before matter as we know it formed, before even space behaved the way it does now. We are asking to peer into the universe when it was so young that time itself may have operated differently. To reach that moment, we must go beyond observation. We must explore theories that push physics to its limits. Because beyond the CMB lies a frontier where light cannot guide us, and where only the mathematics of the early universe can show the way. In the next step of this journey, we confront one of the most powerful ideas in modern cosmology, a moment of expansion so sudden, so immense, so overwhelming, that it reshaped the universe in a fraction of a second. A moment known as inflation. To understand what might lie beyond the edge of our observable universe, we must journey back to a moment so early, so brief that even the word moment is an understatement. A span of time so small that it defies intuition, far smaller than the blink of an eye, far smaller than any slice of time we can imagine. A fraction of a second after the Big Bang, the universe changed in an instant. Space did not merely expand, it erupted. In a period known as cosmic inflation, the universe grew from subatomic size to astronomical scale. In far less than a trillionth of a second, distances between points were stretched so rapidly that regions once close became separated by gulfs larger than the observable universe today. The expansion was faster than the speed of light, not because anything moved through space too quickly, but because space itself ballooned outward at an unimaginable rate. Inflation reshaped everything. It smoothed the universe, ironing out any wrinkles or clumps in the distribution of matter. It cooled the cosmos by stretching it. It set the stage for every galaxy, star and planet that would ever form. The CMB's near-perfect uniformity is its signature. The flatness of the universe is its imprint. The tiny ripples in density, the seeds of the cosmic web, are its frozen echoes. But the most astonishing consequence of inflation is what it tells us about everything we cannot see. When inflation occurred, it did not gently enlarge the universe. It tore apart regions of space that were once adjacent, driving them beyond each other's horizons in an instant. Places that began as neighbours were ripped so far apart that no signal, no particle, no photon could ever cross the distance between them again. The observable universe, everything we can detect with telescopes, is just one patch of a far larger cosmos. A patch carved out by inflation, isolated from the rest of space by distances that light will never overcome. Imagine painting a tiny dot on the surface of a balloon. Then imagine inflating the balloon to the size of the Earth. That dot becomes vanishingly small, lost on a surface millions of times larger than before. This is what inflation did to the universe. It made our observable region a microscopic fraction of a vastly larger whole. And inflation likely did not stop uniformly everywhere. Some regions may have expanded even more than ours. Some may continue expanding even now beyond our cosmic horizon, creating vastly larger structures, perhaps even pocket universes linked only by their shared origin. But even if we consider only the simplest picture, a single universe stretched by inflation, the conclusion is the same. What we see is almost nothing, a sliver of a sliver, a single page torn from a book with infinite chapters. Inflation ensures that the universe beyond our horizon is not just large, it is colossal, far too vast for light to bridge, far too distant for observation to reveal, far too separated for any causal influence to travel between regions. We are cosmic castaways stranded within a bubble inflated so quickly that no message from outside can ever reach us. Inflation answers our question not with speculation but with inevitability. There is more universe beyond what we can see, overwhelmingly more, and we are forever cut off from it. And yet inflation raises another mystery. If our region was stretched into a tiny patch of a much larger whole, what happened to the rest? What shapes exist out there? What physics? What histories? To follow that trail, we must ask whether inflation ended everywhere, or whether it created an endless tapestry of expanding realms. Inflation explains why our universe looks the way it does, but many versions of the theory contain an even stranger implication, one so vast that it redefines what we mean by the universe. In most models, inflation does not stop everywhere at once. It ends in isolated pockets like sparks flickering into existence within a storm. In each pocket, space slows its expansion, cools and fills with matter and radiation. These pockets become regions where galaxies can form, where stars can ignite, where chemistry can unfold, where life has a chance to emerge. Our observable universe is one such pocket, but while inflation slows here, it may continue racing forward elsewhere, pushing distant regions farther and farther away, stretching space at a rate that outpaces everything, faster than light, faster than causality, faster than imagination itself. New pockets form, new regions cool, new universes ignite, and the process continues endlessly. This idea is known as eternal inflation. It paints a picture of reality, not as a single expanding bubble, but as a vast and boiling sea of space, a cosmic foam where bubbles continually grow, collide or drift infinitely apart. Each bubble contains its own pocket universe. Each pocket may have different initial conditions, different ratios of matter, different cosmic trajectories. Some may collapse quickly, some may never form stars, some may evolve in ways so alien that even the laws of physics seem unfamiliar, and all the while the inflating space between these pockets grows exponentially, separating them forever. No light can travel across that gulf, no signal can bridge that divide. Even if civilizations arose in countless bubbles, they would remain eternally isolated, unaware of one another's existence. We live inside one of these bubbles, a tiny region where inflation ended, cooled, and gave rise to galaxies, planets, and observers capable of asking what lies beyond. But beyond the boundary of our bubble lies a realm still dominated by inflation, expanding so rapidly that anything outside our pocket is permanently out of reach. In this picture, the observable universe is not just a small piece of a larger cosmos. It is a microscopic grain on an endless, ever-growing shore. The horizon we see with our telescopes is not the edge of everything. It is merely the point where our bubble fades into the inflating sea beyond. And the inflating sea is not a distant region. It is the background of reality itself, a process still unfolding on scales we can never witness. This does not mean other regions are fantasy. It means they are inevitable consequences of inflation's mathematics. Regions where inflation stopped become universes like ours. Regions where it continues remain forever beyond any possibility of observation. Eternal inflation reshapes our question from what lies beyond the universe we see to how many universes lie beyond the one we see. And if inflation truly is eternal, then the answer may be staggering. Not one, not many, but an unending multitude, each sealed off by horizons that can never be crossed, each with its own story, each a separate chapter in a book too large for any single world to read, In this vision of reality, we're not living at the edge of the universe. We are living in one drop of an infinite cosmic storm. If eternal inflation is real, then beyond our bubble lies not just more space, but regions where the universe itself may be built differently. Inflation creates pockets that cool in isolation, each sealed off from the others by horizons that no light can cross. And within each pocket, the newborn universe unfolds according to its own initial conditions. The laws of physics may be the same everywhere, but their settings might not be. In our bubble, the balance between matter and dark energy allows galaxies to form. Gravity is strong enough to pull stars together, but weak enough to let them burn for billions of years. The forces of nature fall into a harmony so delicate that even a slight variation would erase the possibility of complex structures. If the strength of gravity were a little higher, the universe would have collapsed before stars formed. If it were slightly weaker, stars might never ignite. Change the mass of the electron or the ratio of matter to radiation, and the cosmic web itself would unravel. But in other pockets, the story could be different. Some regions might expand too quickly for galaxies to form, fading into eternal emptiness. Others might collapse almost immediately, swallowed by their own gravity before light even has a chance to shine. Still others might produce stars radically different from our own short-lived titans or cold, dim embers scarcely capable of warming a world. These universes would be real, vast, enormous, and yet forever silent to us. Their horizons stand too far away. Their light will never reach our sky. Their constants, their histories, their entire fabric lie beyond any hope of contact. This leads to a profound realization. We see this universe not because it is typical, but because it is habitable. In a landscape of countless cosmic possibilities, only a narrow range of conditions allows complexity to emerge. If most universes are sterile, empty, or short-lived, then observers will naturally find themselves in the rare pockets where conditions allow stars to shine and chemistry to flourish. This idea is not philosophy, it is logic applied to a multiverse. We can observe only a universe in which observers can exist. This reasoning is known as the anthropic principle, though the name is often misunderstood. It does not claim that the universe was made for us. It claims the opposite, that only universes capable of producing observers will ever be observed. If trillions of bubble universes exist, we inhabit one of the few where the laws of nature permit the emergence of galaxies, planets, and life. But the point is not to argue philosophy. The point is to understand what lies beyond our horizon. If inflation truly created countless regions, then the space beyond what we can see may be unimaginably diverse. Some regions may resemble ours, others may differ in ways we cannot picture. The part of the universe we observe is only a tiny island where the physical constants take values that allow complexity to unfold. In this view, the fine-tuning we see is not an anomaly. It is a selection effect. We live here because here is one of the rare places where life can exist. And all around us, sealed behind the expanding fabric of space, may lie realms where the story of creation took a different path. Some bright, some barren, some brief, some eternal. We look at our universe and see harmony, but beyond our cosmic horizon may stretch a vast orchestra of universes, each playing a different song. Even if we set aside the idea of multiple universes, the cosmos we see through our telescopes is only a fragment of something vastly larger. The observable universe is not the universe itself. It is simply the region from which light has had enough time to reach us since the birth of space and time. Imagine standing at the center of a growing sphere of visibility. At the moment of the Big Bang, that sphere was exactly zero. As the universe aged, light began its long journey toward us, filling the sphere with information. Today, after more than 13 billion years, that sphere has grown to a diameter of 93 billion light-years, not because the universe is that young, but because space itself has expanded while the light traveled. This sphere is not a physical bubble floating in space. It is a horizon of knowledge, a limit set by the finite speed of light and the finite age of the cosmos. Everything inside the sphere is visible in principle. Everything outside is shrouded in permanent darkness, not because it is different, but because its signals have not and in many cases cannot reach us. This leads to a simple but profound realization. When we speak of the universe, we're almost always talking about the part of it that light allows us to witness. But there is no reason to believe that the universe ends where our observations end. The universe existed long before its light reached us, and it continues far beyond the distance that photons can cross. The observable universe is therefore a bubble of information floating in a sea of unknowable space, a boundary drawn not by matter or gravity, but by the speed at which signals can move. If the cosmos had begun 1 trillion years earlier, our horizon would be vastly larger. If light could travel faster, we would see more. The limits we perceive are not cosmic boundaries. They are constraints imposed by the nature of time itself. This misunderstanding has profound consequences. Many imagine the observable universe as the whole of existence, a self-contained sphere beyond which lies emptiness. But the truth is far more humbling. The sphere we see is tiny compared to the universe's full extent. If the cosmos is infinite, then our horizon is like a drop of water scooped from an endless ocean. If it is finite but unbounded, our horizon is like a flashlight beam sweeping across the surface of the Earth, limited by reach, not by terrain. An expansion complicates the picture even further. As space grows distant, regions recede faster than light can bridge. Some galaxies we see today are already beyond our reach. Their future light will never arrive. The horizon is not static. It is drifting outward, leaving more and more of reality permanently inaccessible. What we observe is therefore a fleeting snapshot of a much larger stage, a momentary glimpse at structures that will eventually vanish beyond the limits of contact. So when we ask what lies beyond the observable universe, the honest answer is that nearly all of reality lies beyond it. Not metaphorically, literally. The cosmos we can study is a finite window carved out of something far larger, shaped by the physics of light, time, and expansion. And that horizon forces us to rethink our place in the universe. We are not at the center of everything. We are simply at the center of what we can see. Beyond that, the universe continues in ways we can measure, indirectly infer from theory, or only imagine. The horizon does not define the universe. It defines our limit within it. When we talk about the edge of the observable universe, we're usually referring to a specific boundary. The particle horizon, the greatest distance from which light has had time to reach us since the beginning of the cosmos. It marks the radius of the sphere we can see, a limit drawn by the age of the universe and the speed of light. But the particle horizon is only half the story. There is another boundary more subtle and more unsettling. The event horizon, the farthest distance from which light will ever be able to reach us in the future, no matter how long we wait. It is shaped not by the past, but by the expansion of space that accelerates with time. These two horizons are not the same. They do not overlap, and that difference reveals something remarkable about our place in the universe. The particle horizon tells us how far back we can see. It shows the faintest galaxies, the earliest structures, the ancient glow of the cosmic microwave background. But the event horizon tells us something more profound. Which parts of the universe remain connected to us, and which parts have slipped beyond our influence forever. Because the universe is expanding and that expansion is accelerating, galaxies at great distances are being carried away faster than light can bridge the widening gap. Their light today still reaches us because it was emitted when they were closer, but their future light, the light they are emitting right now, will never arrive. The expansion of space outruns the photons trying to cross it. This means that when we look into the night sky, we are seeing ghosts, not illusions, real galaxies, but galaxies whose present forms we will never witness. Their light is on the way to nowhere. Their fate is sealed by the relentless growth of space. The particle horizon encloses the region we can observe. The event horizon encloses the region we can ever communicate with. Everything beyond that event horizon is drifting away so rapidly that no message, no probe, No beam of light can ever cross the distance in either direction. The consequences are startling. Some galaxies within our observable universe are already lost to us. We can still see the light they emitted billions of years ago, but we can never influence them and they can never influence us. They are permanently cut adrift, isolated by the expansion of the cosmos. If our galaxy were to broadcast a signal today, a pulse of light, a radio message, or any form of electromagnetic communication, entire regions of the observable universe would never receive it. The message would chase them forever, always losing ground, always falling behind the receding horizon. In the distant future, this isolation becomes even more severe. As expansion continues, more and more galaxies will cross the event horizon and vanish from sight. The night sky will slowly empty. The cosmic web will fade into darkness, leaving only the galaxies gravitationally bound to our own. We often imagine the visible universe as a stable, fixed arena, but the truth is that our cosmic horizon is dynamic, a shifting boundary defined by the expansion of space. The universe we see today is not the universe we will see tomorrow. Every year more of it drifts beyond reach, and so the question what lies beyond the universe we can see gains a new dimension. Beyond our horizon lies not only space too distant for light to reach us, but space being pulled away so quickly that it is forever sealed off, locked behind a horizon that grows with time. We are not just limited observers. We are inhabitants of a cosmic island slowly being separated from the rest of the universe. Our horizon defines the shrinking portion of the cosmos with which we remain connected. Beyond it lies the unreachable, the unobservable, and the forever unseen. As the universe continues to expand, a slow and quiet transformation unfolds across the sky, a transformation so gradual that no human will ever witness it, yet so profound that it reshapes the very meaning of the cosmos. Today the night sky is alive, galaxies swirl across the darkness. Clusters shine as distant beacons. The cosmic web stretches outward in every direction, glowing faintly with the light of trillions of suns. But this view is temporary. Over the next tens of billions of years, the expansion of the universe will push every galaxy beyond our gravitational neighborhood farther and farther away. One by one, they will dim. Their light will stretch into longer wavelengths, fading into the infrared, then into microwaves, and finally into silence. Eventually, they will slip beyond the cosmic event horizon, entirely carried away by expansion faster than their light can travel. To future observers, the sky will look almost empty, not because the universe ran out of galaxies, but because the galaxies ran out of time to be seen. The Milky Way and Andromeda will have merged into a single massive galaxy. The smaller members of the local group will orbit this new colossus like faint companions. Beyond that, the sky will be black, featureless, without a hint of the grand cosmic structures we see today. Even the cosmic microwave background, the oldest light in the universe, will fade. Its wavelengths will stretch until they are larger than the horizon itself, slipping beyond detection. The last evidence of the Big Bang will evaporate into the darkness. Cosmology as we practice it today will become impossible. Imagine a civilization born in that distant era. They look into the sky and see a single galaxy, their own, suspended in an endless void. No other galaxies, no cosmic web, no expanding universe, no CMB, no clues. Their universe appears small, static, and eternal. They may search for evidence of a beginning, but the traces will be long gone. To them, the cosmos will seem self-contained, a lone island surrounded by infinite emptiness. They will never know that beyond their dark horizon lies a vast universe filled with galaxies that once shone brightly. Galaxies we see today, but that their future eyes will never witness. They will never suspect that the cosmos had a beginning, or that it once blazed with radiation, or that it expanded faster than light. Without the CMB, without distant galaxies, without redshift, the clues we take for granted will be erased. The universe will hide its past. This future, lonely and silent, reveals a deep truth about the horizon. It is not just a limit of observation, but a limit of knowledge. As expansion accelerates, it erases the evidence of what the cosmos once was. The universe grows, but our window onto it shrinks. And so when we ask what lies beyond the universe, we see we must remember that even the universe we see today is only temporary. Galaxies we observe now are already slipping beyond reach. Structures we map today are destined to disappear. The cosmos is not static. It is slipping away from us one horizon length at a time. We live in a privileged moment in cosmic history, a moment when the universe is still young enough to reveal its vastness, yet old enough for us to understand it. Future observers will not have that privilege. They will live inside a cosmic island unaware of the ocean beyond. The sky grows emptier with time, but the universe does not. It continues. Beyond the horizon, beyond our vision, beyond the future's silence, we stand inside a universe wider than imagination. Yet the part we can see is astonishingly small. Our cosmic horizon encloses a sphere of light, a thin shell carved out by time and physics. Beyond it stretches a realm we will never witness. Not because it hides from us, but because reality itself forbids the light from reaching our eyes. And yet this limitation is not a flaw. It is the way the universe is built. Every observer, no matter where they live, is trapped within their own horizon. A galaxy 10 billion light-years away has its own sphere of visibility. A civilization living in a distant cluster sees a different slice of the same vast universe. Each horizon overlaps with others like lanterns glowing in an endless night, illuminating small patches of a landscape too large for any single light to reveal. We see only a fragment, but that fragment is rich with clues. Patterns in the cosmic microwave background, ripples in the distribution of galaxies, the quiet fingerprints of dark matter and dark energy, gravity's subtle pull on the shape of space. Each clue is a message from the universe carried across billions of years, telling us something about the parts we cannot see. And this is the paradox of cosmology. Though our vision is finite, our understanding can be far greater. We cannot observe the regions beyond our horizon, but we can infer their existence through the consistency of physics. The laws that govern our part of the universe operate with such precision, such uniformity, that they almost certainly apply elsewhere. The smoothness of the cosmic microwave background suggests that the universe beyond our view is not chaotic. It is structured, it is coherent, it obeys the same cosmic rules that shaped our own corner of space. Mathematics becomes our telescope, theory becomes our window, patterns become our guides. By studying the universe, we see we can map the universe we cannot. Inflation tells us that space beyond our horizon looks much like space within it, or that it may follow different trajectories shaped by ancient quantum fluctuations. Expansion tells us that vast regions once close to ours now lie beyond all contact. Geometry tells us whether the universe curls, stretches, or extends without limit. Horizons tell us where understanding ends and where imagination must take over. We are not helpless before the unknown. We are shaped by it. The universe is too large for us to see in its entirety, but not too large for us to reason about. In the absence of direct observation, we build models, test predictions, search for patterns, and let the laws of nature speak for themselves. Even when light fails, physics continues the story. And this is perhaps the most humbling truth of all. The parts of the cosmos we will never observe are not unreachable, because we are small, but because the universe is vast beyond all comparison, vast beyond any need for an observer. Our horizon is not a prison, it is a frame, a boundary that defines the region from which information can reach us, and a reminder that the universe is not obligated to reveal itself in full. Beyond that boundary lies a realm that follows the same laws shaped by the same origins, unfolding through the same cosmic history, even if we will never see it with our eyes. And as we move toward the final steps of this journey, we begin to face one last question. If the universe hides so much from us, what does it mean to understand it at all? What lies beyond the edge of our cosmic horizon? The truth is both simple and overwhelming. Almost everything. All the galaxies we cannot see. All the clusters that light will never reach us from. All the regions inflation carried beyond our ability to detect. All the matter and energy shaped by the same physics that governs our visible world. The universe does not end where our observations end. Our horizon is not a boundary of existence, only a boundary of information. Beyond it, the cosmos continues indifferent to whether we can witness it. According to the cosmological principle, the universe should look roughly the same everywhere on large scales. If that principle holds, then beyond our horizon lies more of the cosmic web filament stretching into deeper darkness, voids yawning larger than imagination, clusters swirling in gravitational dances too slow for any living creature to perceive. The patterns we see here would repeat endlessly, a grand structure extending far beyond the reach of light, and inflation strengthens that idea. It suggests that the region we observe is only one small patch in a much larger expanse that was once connected but has since drifted beyond communication. The same forces that shaped our corner of space must have shaped countless others. The same fluctuations that seeded our galaxies also seeded galaxies far beyond our sight. In this view, the universe beyond our horizon is not exotic. It is simply more universe stretched to distances we will never cross. Yet physics also leaves room for strangeness. Quantum fluctuations during inflation could have nudged distant regions in different directions, altering their densities, their expansion rates, or their cosmic histories. Far away, the universe might not mirror ours exactly. It might contain vast stretches with fewer galaxies or far more, regions where structure formed earlier or later or not at all. The laws themselves may be the same, but the outcomes could differ in ways we cannot imagine. But whether the unseen universe is familiar or foreign, one thing is certain. We cannot reach it. This is not a technological barrier, not a challenge waiting for future engineers to solve. It is a fundamental feature of reality, a consequence of relativity expansion and the speed of light. No spacecraft can outrun a horizon receding faster than light. No signal can bridge a gap that grows larger with every passing moment. No future observation will capture the light from regions permanently swept away by inflation. We live within a cosmic island, its shores defined not by geography, but by the laws of physics, and yet even from this island we can sense the contours of the greater ocean. We can infer the shape of the universe from the patterns we observe. We can model the early conditions that gave rise to the regions beyond. We can trace the fingerprints of processes that unfolded across the entire cosmos, even if only a tiny portion is visible to us. This is the triumph of cosmology, that from a single patch of sky, we can reconstruct the history of a universe far larger than our horizon. We can understand its birth, its evolution, its structure, and its fate, even though we will never witness most of it firsthand. But this triumph brings with it a profound humility. For every galaxy we observe, countless more lie hidden. For every structure we map, untold superclusters stretch out of reach. For every era we reconstruct, there are timelines we will never access. Our universe is larger than our ability to see, older than our ability to measure, and deeper than our ability to comprehend. And as we approach the final chapter of this exploration, we confront the hardest truth of all. The universe beyond our horizon exists, but it is fundamentally unknowable. At least, unknowable in the traditional sense. But perhaps there is another way to understand what lies beyond. We will never see the whole universe. No telescope, no probe, no technology imaginable can carry us beyond the horizon that surrounds our world. The expansion of space ensures that vast regions of the cosmos remain forever hidden, receding faster than any signal can travel. The universe keeps its distance, and its deepest secrets lie locked behind horizons we cannot cross. And yet this is not a tragedy. It is a revelation. The limits of our vision remind us that the universe is not shaped for our convenience. It is not scaled to our senses or tailored to our understanding. It is immense because it can be. It is ancient because it must be. It stretches beyond our reach, not to taunt us, but because reality is under no obligation to be small. Even within this narrow window of light, we have uncovered wonders. We have mapped the structure of galaxies spread across billions of light years. We have decoded the faint glow of the cosmic microwave background, a whisper from the dawn of time. We have measured the curvature of space, the expansion of the cosmos, and the traces of inflation etched into the universe itself. From a tiny patch of sky, we've reconstructed nearly the entire story of creation. This is the triumph of being human, our ability to reach beyond what we can see, to infer the shape of the unseen, to imagine the parts of the universe that light cannot touch. The horizon does not diminish our understanding, it defines it. Within that boundary, we read the universe like a book whose first and last chapters are missing, yet whose middle pages reveal enough to glimpse the larger narrative. We will never hold the full volume, but we can understand the story, and perhaps that is enough. Beyond the horizon lies a universe that is real but unknowable, a universe that continues without us, indifferent and vast, a universe whose galaxies drift forever out of view, whose ancient light will never reach our world, whose history unfolds in darkness. But here in this small island of visibility, something extraordinary has happened. A species arose capable of asking what lies beyond the edge of everything. A species capable of building instruments that catch photons older than galaxies. A species capable of tracing the contours of a cosmos that dwarfs them in every way. We are small, but our curiosity is not. We are brief, but our questions are not. We are limited, but our imagination is boundless. When we look toward the horizon, we do not see the end of the universe. We see the beginning of mystery. We see the frontier of knowledge. We see the place where exploration becomes wonder. And beyond that horizon, beyond the light that reaches us, the universe continues, endlessly, silently, majestically, not waiting for us, not depending on us, simply being what it is, a cosmos far larger than what we can see and far deeper than what we can know. The deeper we look into the universe, the more clearly we realize a simple truth. The cosmos is not built for us. It does not bend to our senses or reveal itself fully to our eyes. It expands, evolves, and stretches into distances we cannot cross, guided only by the laws of nature and the passage of time. And yet, standing on this tiny world orbiting an ordinary star, we dare to ask what lies beyond everything we can see. It is a question that no other species on Earth has ever asked. A question that no other creature, as far as we know, has ever understood how to form. A question that reaches beyond survival, beyond instinct, into something deeper. A need to trace our origins, our limits, and our place within something far larger than ourselves. The universe does not grant us easy answers. It shows us only a sliver of itself, a thin sphere of light defined by the speed of photons in the age of time. Outside that sphere, the cosmos continues without hesitation, indifferent to our presence. Expansion pushes galaxies farther away. Horizons grow, histories unfold in darkness. But the fact that we cannot see the whole universe does not diminish its meaning. It enhances it, because the unknown is not a void. It is a frontier, a reminder that there is more to existence than what reaches us. More than what our instruments can measure, more than what our theories can fully describe. The universe withholds most of itself, and yet from the part we can see, we've uncovered extraordinary truths. We have watched stars live and die, measured the curvature of space, traced the glow of creation, and mapped structures spanning billions of light years. We've pieced together the story of a cosmos far vaster than our horizon, using clues carried across the ages, and in doing so we have discovered something profound. Understanding does not require completeness, meaning does not require total knowledge, wonder does not depend on seeing everything. We will never know what lies beyond the ultimate horizon, not with certainty, not with light, not with any tool bound to the laws of physics, but perhaps that is the point. The universe is not a puzzle to be solved. It is a reality to be witnessed. Its mystery is not an obstacle, it is a gift. A reminder that even in a world governed by equations there is room for awe, and so we continue to look outward knowing the view will always be incomplete. We continue to ask questions knowing the answers may forever remain just beyond reach. We continue to explore not because the universe needs to be understood, but because we need to understand it. For as long as there are minds to wonder, the horizon will never be the end. It will be an invitation, a silent promise that the universe contains more than we can imagine, and that the pursuit of knowledge is itself a journey without limits. Even when the cosmos refuses to reveal what lies beyond its farthest edge, it gives us something just as powerful: the curiosity to keep searching, the imagination to keep asking, and the courage to face the infinite. In the end, the universe does not owe us clarity. It does not promise that every question can be answered, or that every horizon can be crossed. Most of its expanse will remain forever hidden, sealed behind the physics that shaped it. The light from distant galaxies will never reach us. The echoes of ancient eras will fade into silence. The greater cosmos will continue in darkness, indifferent to whether anyone is there to witness it. And yet we still look up. We look not because we expect the universe to reveal its secrets, but because looking is what we do. Because curiosity is the one force in the universe that expands faster than space itself. Because even a small glimpse of the cosmos is enough to transform the way we see ourselves. Because in a universe filled with unreachable horizons, the very act of wondering becomes a kind of light, a signal that crosses distances physics cannot close. We may never know what lies beyond the farthest edge of sight, but we know this. The universe is larger, stranger, and more magnificent than anything our senses can hold. And as long as there are minds willing to ask the impossible, the horizon will not be an ending but a beginning. So we continue, we observe, we imagine, we dream. And somewhere beyond the limits of light and time, the universe goes on vast, silent, eternal, waiting for us to ask the next question,